Thanks for joining me in today's lesson. In this first tutorial, we will understand all parts of the definition of a limit, and we will find the limit from a graph or using our calculators. So, congratulations, you've made it to our final chapter of our pre-calculus year. We're in section 13.1, and I'd like to warm up with this problem. We have 24 feet of wire, and we need to form a rectangle whose area is as large as possible. What should the dimensions be? What I'd like to do is start by drawing as many different rectangles as I can that basically have a perimeter of 24 feet. So I'm going to start with the little guy here, and we'll make the dimensions 1 by 11. That's a width of 1 and a length of 11. Therefore, its perimeter would be a 12 and another 12, which of course is a perimeter of 24. The area of this is 11 square feet. Sounds good. Maybe we move up to the next one. If we have a width of 2, these are not necessarily going to be to scale. So a width of 2 would have to have a length of 10 for us to have a perimeter of 24. And that area is larger, so therefore it's winning. 2 times 10 would be 20. Let's see what happens when we increase the width to 3. Therefore, our length would be 9, and that has an even larger area, 27 square feet. Okay, so we're getting bigger. Let's try 4. And what do we have over here? If we do 4 by 8, then our area is going to be 32, even larger. Let's try 5. I guess I'll do that right here. This would be a 5 by 7, almost a square. And this would have an area of 35 square feet. Okay. So can I do a square? Could I do a 6 by 6? Let's try 5.5. It doesn't say that I have to have integer sides. What if I did 5.5 by 6.5? That would work too, wouldn't it? 5 by 5, or excuse me, 5.5 by 6.5. And that area is indeed larger, and I think it's 35.75 square feet. Question is, could I do a square, 6 by 6? Is that a rectangle? Because that does have a very large area. In fact, it has the largest one that we could have, 36 square feet. And yes, this is a rectangle. The definition of a rectangle, you have to have 4 sides and you have to have 4 right angles. So a square is a rectangle. So this is a nice illustration of today's topic, which is limits. Let me write the symbol for the limit that we are basically describing here. So the limit symbol has an LIM. This is our limit symbol. Directly underneath this is what our variable is approaching. And I'm going to talk about the width since we're talking about rectangles. And I'm going to say that the width is approaching 6, which is our final winning width. The largest area comes from when the width is 6. So the limit as w approaches 6. And our function, I'm just going to say it's an area function, the area in terms of the width. So a of w. This limit is equal to 36. So this is our symbol. All of this is in one line. The L, the I, the M, the A of W, the equals, and the 36, all in one line. It's just that this part of the symbol is directly underneath the LIM, but that's how you write this symbol. Let's describe, or let's talk about what this means. Ultimately, we're saying that the limit is 36. Therefore, the area, since we're talking about area, is 36. And it's the limit as our width is approaching 6. Okay, so if we go to the tiniest of our widths, which was the 1, we get the tiniest of our areas. If we start to increase our width from 1 to 2 to 3 to 4 to 5 to 5.5 to 6, you can see that the areas are growing on their way to 36. And on the other side of the width, if we start with the largest width, which was 11, again, that happens to give us our smallest area. And if we start decreasing our widths, if we call this the width, from 11 to 10 to 9 to 8 to 7 to 6.5 to 6, we can also see that the areas are getting closer to our final answer of 36. So that's what a limit is. A limit is what's happening on either side of the variable, of the number that we are approaching. On either side of this value of 6, we're getting closer and closer and closer to 36 for our area. So it's important to see what's happening on the left side of 6, the lower numbers, and it's also important to see what's happening on the right side of 6, the greater numbers. And as we approach 6, our limit becomes 36. So let's look at our first example. We want to evaluate this limit. It says the limit as x approaches 2 of, here's our new function, 3x minus 2. So what we need to do first is we need to figure out what's happening on the left side. And we're just going to do a quick little t-table. So our t-table is going to have x, and we'll plug that value into our 3x minus 2. So we want some values that are on the left side of 2. So we want, a lot of people say, oh, let's put 1 in there. Well, if you think about it, we want numbers that are really close to 2, and 1 is not particularly close to 2. It's an entire tick mark away. So maybe 1.9. I'll do 1.99. That's even closer. Maybe I'll do 1.9999. I'll do 5 nines here. Now that's a number that's very close to 2. What I need to do with these numbers as we're getting closer to the value of 2 on the left side is plug these numbers into my function and see what happens. I'll plug the 1 in and I actually get a 1 out, and that doesn't matter. 1.99 though, that's pretty close to 2. If I plug 3 times 1.99 minus 2, I'm going to have about 3.97, I believe. Yes. If I plug in 1.99999, just into our calculator, 3 times that minus 2 gives us 3.99997. So as we're getting closer to 2 for the x, it looks like our value of the function is getting closer to the number 4. Let's see what's happening on the right side, because we're interested on both sides. Same thing, we've got our x's, and we're going to be plugging it into 3x minus 2. So let's get some numbers that are close to 2 but on the right side of 2. For example, 2.1. That's close. Or maybe 2.001. Or maybe even 2.1234. It's 4 zeros and a 1. How about that? Plug these numbers in to our function, and we're going to get numbers like 4.3 and 4.003 and 4.00003, I believe. So you can see clearly from our quick little t-tables that when we're on the left side of 2, again, 2 is the thing that we're trying to approach. That's what x is approaching. As x approaches 2 on the left side, our function is approaching the value of 4. And on the right side, as x is approaching 2 on the right side, it's getting closer and closer and even closer to 2, the function is getting closer and closer and even closer to 4. So you would think, of course, that this limit is equal to 4, and you'd be correct. Now, some of you might say, well, isn't there a whole lot faster way of doing that? Can't I simply plug a 2 right into the function and get 4? Sure, 3 times 2 minus 2 is equal to 4. But the point is, that will not always work. This is called direct substitution. And if you can do direct substitution, that would be great. Go ahead and do that. If you cannot, you have to understand the technique that I'm about to show you in example 2. This time we are finding the limit as x approaches 1 of this function. Now, some of you might say, well, let's just plug in a 1. Sure, you can go ahead and plug in a 1, but you're going to see that when you plug a 1 into this denominator, 1 minus 1 equals 0. You cannot divide by 0. That does not mean that the limit doesn't exist. That just means we need a different technique to find it. So we're going to need our calculators today. Now, we could do it by hand, all these t-tables, and I really don't want to do that. I'm going to use the calculators table. So get your calculators out, and in fact, I'd like for everybody, just so we're all talking at the same on the same screens, I'd like for everybody to push on their calculator second, and then the plus sign, and then the 7, and then the 1, and then the 2. That will reset your RAM, and then we'll all be looking at the same screens. Let's clear this out. I'm going to push second, and then the plus sign gets me into my memory stuff. 7, and then 1, and then 2, and my calculator's been reset. Excellent. So what I want to do is use this calculator, I'll slide this over a little bit, use this calculator and plug this function into the calculator. I'm just going to plug it into y1 as if I'm going to graph it, but I'm interested in looking at the table. So I'll go put it into y1. Let's do that. So I'm going to go to the y equals, of course I need parentheses around the entire numerator and the entire denominator. So I've got my x cubed minus my x squared plus my x minus 1. Close that parenthesis, and then I'll divide by my denominator, which is x minus 1, and I've plugged this function into my calculator. Now I'm interested in looking at the t-table, and the table is right here in blue above the graph button, so I'm going to push second table, and I'm looking at the table. Now, interesting, I get an error when x equals 1. And that's, of course, because we cannot divide by 0. And that's the reason why we're doing this technique in the calculator, because I'm interested in 1, and that's the 1 number I can't plug in, unfortunately. So I need to see what's happening to the left of 1 and to the right of 1. But I'm nowhere near those numbers because this table is counting by ones. So what I want to do is change the table set, and that's above your window button in blue. So I'm pushing second table set. You can see that my table change, my delta table, I'm counting by ones. I don't want that to happen. I want to count by tiny numbers like 0.001. That's what I'm going to count by 0.001s. I also want to make sure that I'm starting my table where I want to be seeing the value, which is 1. I don't want to start at -2. I want to start at 1. So I'm changing my table to count by very tiny amounts, and I'm centering my table at the value of 1. Now when I go back to second table, I can see, of course, my error, and I'm going to push up a few so I can see the numbers that are getting close to 1 on the left side. I can see what the function looks like it's approaching. And the numbers on the right side, as I get closer and closer to 1, I can see what the function is approaching. Do you see what it's approaching? It's approaching the value of 2. So this limit is equal to 2. So for your notes, you might want to put in those calculator steps. We went to second and then table set. That's how we can manipulate what we want our table to do. For the table start, we chose 1, and that's because we're talking about the limit as x approaches 1. And for our delta table, we chose to count by 0.001, very tiny numbers. So this is a technique that you can use your calculator. Now this is only needed for when you cannot plug your value into your denominator ultimately. You do not need to do what we did here. I was just illustrating that for you. If you can just do direct substitution and get an answer, then that is your limit. If you cannot do that, then you can use your calculator technique, or you can use a later technique that I'll teach you in a later tutorial. So here's our definition of limit. If f of x, our function, becomes closer to a number L as x approaches some domain point C from both sides, and it's important that we're approaching from both sides, we'll talk about that a little bit later, then the limit will be this symbol. The limit as x approaches that domain point C of our function is equal to L. That's the definition of our limit. Now we have to be approaching from both sides of this domain point C, and then the limit will be equal to this number L. So here's our first try, and I'd like for you to pause the video and use your calculator to find this limit. Now, of course, I've already given you the hint. You can't plug in the 0 because I said you must use your calculator. So practice this on your calculator. You're going to have to change your table around and then unpause and see if you got the correct answer. Pause now, please. When you plugged this into the calculator, you needed to change your table set to start at 0 and still count by that tiny amount, and you should have gotten your answer as 8. I want you to understand that this function that you just used the calculator for will never actually be equal to 8. But that's not what's important. What's important is, what is this function approaching? What value are we trying to become? Not what value will we actually become, but what value are we trying to become? And that is the value of 8. And that's explained over here. And this is an important page right here with this graph. The existence of a limit does not depend on if f of x is actually defined for that domain point. So for example, we're looking at this graph, and we'll just call this the graph of f of x so we can talk about these symbols here. And here's the graph of f of x. The main one that I'm interested in right now is, what's the limit as x approaches 1 of this function f of x? So here is when x equals 1 right here, and what we want to do is, if we're looking for a limit, we need to get on both sides of that value. And so we need to get on the left side and get closer and closer and closer to 1, and we need to get on the right side and get closer and closer and closer to 1. So as we're getting closer and closer, the function appears to be approaching this open dot. And as we are on the right, the function appears to be approaching this open dot. And that's exactly what this function is trying to become, this value of 2. And that's why this limit is equal to 2. I don't care if the function is actually defined right here or not. Sometimes it'll be an open dot, sometimes it'll be a closed dot. It doesn't matter what this dot actually is doing. What matters is what the function is doing, getting closer and closer on the left side, getting closer and closer on the right side. Now, I clearly can see that the function is actually equal to 3 when x equals 1. But I could care less what happens when x equals 1. I care what's happening as we get closer to 1 on each side. So I do know that f of 1 is equal to 3, but that really doesn't matter for my limit. My limit is equal to 2. Now I'd like to find another limit that's equal to 2. And I can see that this function is equal to 2 about right here again, let's say. So we're talking as x approaches 1, 2, 3, 4. So the limit as x approaches 4 of f of x is also equal to 2. Now this actually equals 2 as well, because we actually have a nice closed dot. Again, that doesn't really matter though, as long as when we're getting closer to closer to 4 on the left side and closer to 4 on the right side, our function is approaching this dot. And it happens to actually be that f of 4 is equal to 2. There's one other time on this graph where the limit would be equal to 2, so I'll just keep using an equal sign. And we're equal to 2 there, we're equal to 2 here, even though we don't actually touch it. And let's say approximately right there, the function is equal to 2 as well. That looks like when x is negative 2. So that means that the limit as x approaches negative 2 of f of x is also equal to 2. I'm just going to circle that since that's the main answer. The left side, we're approaching 2. The right side, we're approaching 2. And again, it actually is equal to that if we plugged in the number negative 2 into our function. So again, it's very important to understand that I don't care if it's an open dot or if it's a closed dot, the function is approaching infinitely closer to the left, infinitely closer to the right. That's what it's becoming, and that's what the limit is. I do have one more symbol down here that I'd like to look at. What's the limit as x approaches negative 4? Well, it's pretty simple. Let's go to -4. Here's -4. What's the function approaching? Well, on the left side, it looks like we're trying to get to this point right here. On the right side, we're trying to get to this point right here. That limit is equal to 0. So this is an important page to look at. And that ends this first tutorial. I'll see you in class to practice this, and I'll see you in the next couple tutorials. Thank you.